evaluate definite integrals analytically, sometimes it's very difficult or even impossible to determine a function's antiderivative. So when the analytic method fails, we use a numerical approach to approximate a definite integral. And the trapezoid rule is a numerical method to approximate a definite integral using trapezoids. Let's take a look at how this is going to work. Let's say we want to use a trapezoid to approximate the definite integral of this function on the interval from 0 to 8. You can see if we use one trapezoid in green, this area is much larger than the area bounded by the function in the x-axis, represented by the definite integral. However, watch what happens as we increase the number of trapezoids. You can quickly see that as we increase the number of trapezoids, the sum of the area of those trapezoids is going to approach the value of that definite integral. Let's go and take a look at another function. Again, watch as the number of trapezoids increases. You can see it quickly approaches the value of that definite integral on the given interval. Okay, let's go back to our presentation. Let's do a little review first. Remember, a trapezoid is a quadrilateral with one pair of parallel sides. So to determine the area of a trapezoid, we have the area equals 1/2 times the quantity of base 1 plus base 2 times the height, and this would be the diagram. However, we're going to be using right trapezoids, which means we have two right angles in the trapezoid. The trapezoid will also be rotated from what we're used to seeing. So this will be base 1 and base 2, and the height would be the length of this side here. Let's say we wanted to approximate this definite integral in yellow by using 4 trapezoids on the interval from A to B. Well, first, if we have 4 trapezoids, that means n is going to equal 4. So what we would do is we want to divide this interval into 4 equal parts. And one way to do that would be to take the length of the entire interval, or b minus a, and then divide it by n. So when we divide the interval into 4 equal parts, because our n is equal to 4, this would be a, which we'll call x sub 0. This would be x sub 1, x sub 2, x sub 3, x sub 4, which is also equal to b. We have 4 equal intervals. Next, what we would do is construct our 4 trapezoids. So they would look like this. So our first trapezoid, our second trapezoid, our third trapezoid, and our fourth trapezoid. And we can see this is going to be a pretty good approximation of this definite integral. Let's go ahead and label this trapezoid 1, trapezoid 2, 3, and 4. Remember, the area for a trapezoid is 1/2 times the quantity base 1 plus base 2 times the height. But we're going to go ahead and use it in this form. We'll have the height times base 1 plus base 2 divided by 2. So to approximate this definite integral, we'll determine the area of these 4 trapezoids, where these function values would be the bases of the trapezoids, and the length of each x interval would be the height. And notice they're all equal to each other, and so we can use the formula b minus a divided by n to represent each height of the trapezoid. So we'd have the height times the sum of the two bases divided by 2 for the area of trapezoid 1. That'd be f of x sub 0 plus f of x sub 1 divided by 2. So this product here would be the height times half of the sum of the bases. So this would be the area of trapezoid 1. Since the height is the same, we'll just write the sum of the two bases divided by 2 here for the second trapezoid. Well, that would be f of x sub 1 plus f of x sub 2 divided by 2. So this product would be the area of trapezoid 2. For trapezoid 3, we have f of x sub 2 plus f of x sub 3 divided by 2. And then for the last trapezoid, we have f of x sub 3 plus f of x sub 4 divided by 2. Again, each of these products, when we distribute, represents the area of each of these trapezoids. So when we find the sum of those, that'll approximate the area of this definite integral. Now let's go ahead and take a look at one more thing. Notice they all have a denominator of 2, so we could factor this 2 out. So we would have b minus a divided by 2n. And notice that there are two f of x sub 1's, two f of x sub 2's, and two f of x sub 3's. So simplifying the numerator, we would have f of x sub 0 plus 2 f of x sub 1 plus 2 f of x sub 2's and 2 f of x sub 3's, and we have 1 f of x sub 4. So I want you to notice the pattern of these coefficients. We have 1, 2, 2, 2, 1. So we'll always start with a coefficient of 1, then we'll have 2's, and we'll end with a 1, regardless of what n is. Let's go ahead and formalize the trapezoid rule. Using the trapezoid rule, we can approximate this definite integral using this formula, and this formula represents the area of a certain number of trapezoids based upon the value of n. And again, I want you to notice that we have 1 f of x, 2, 2, 2, and so on, but we end with a 1 as well. So as n approaches infinity, the right hand is going to approach.
In the formula, we have multiples of 2. We have 2 fx sub 1, 2 fx sub 2, up to 2 fx sub n minus 1. We can factor out 2 from all of these terms. When we factor out 2, we have b minus a over 2n times fx sub 0 plus fx sub n plus 2 times the sum of fx sub 1 up to fx sub n minus 1. We know that b minus a over n is the height of the trapezoid. Here we denote it as h. H is also known as the width of the subinterval. Therefore, h can be written as b minus a over n. And if we let y equal to fx, the formula can be written as h over 2 multiplied by y sub 0 plus y sub n plus 2 times the sum of y sub 1 up to y sub n minus 1.